Okay, guys, so let's do example 2 from section 11.1, part 2. Just another chi-square goodness of fit test. Okay, so biologists wish to cross pairs of tobacco plants having genetic makeup GG, indicating that each plant has one dominant gene and one recessive gene for color. Okay, each offspring plant will receive one gene for color from each parent. The following table, often called a Punnett square, if you've done biology, you've seen this. A Punnett square shows the possible combinations of genes received by the offspring. All right? So, what does this tell me? So the Punnett square suggests the expected ratio of green, okay, to green-yellow, or yellow-green, to albino tobacco plants should be 1, 2, 2, 1. In other words, if I take a huge group of these plants, this should be the distribution I see in that group. What that means is for every one GG, capital G, I should see 2 capital G, lowercase g, and 1 lowercase gg, okay? Which basically results in these proportions, these 3 proportions, okay? So, and you can think about it this should be 100% of the distribution, but there's 2 of these, and 1 of this, and 1 of this. So this must be 50%, and this must be 25%, and this must be 25%. Okay, I think that's fairly clear. So that's actually our hypothesis. Our null hypothesis, or the claim is that this is the distribution, oh, not that, sorry, that this is the distribution of genes. Okay, so the test hypothesis about the distribution of the offspring biologists mate 84 randomly selected pairs of yellow-green parent plants. Of 84 offspring, 23 were green, 50 were yellow-green, 11 were albino. Do these data significantly differ from what biologists have predicted? So their claim of 25, 50, 25, okay? Carry an appropriate test at that significance level. All right, so let's do it. So we say state, we want to perform a test of, and I think I'm going to go with the other way around of doing this. Okay, let's do the null hypothesis is that P sub green is 0.25, that's this one, okay, and then P sub yellow green, okay, something like that, is 50%. I apologize for my ugly 5. And P sub albino is also 25%. Then my alternative hypothesis will be what? At least one of the P subcolors is incorrect. Okay? At least one of the P subcolors is incorrect. Okay? Is incorrect. And that's it. And now we have to define this. Since we used this, we have to define it. So we say where P subcolor is the true proportion of tobacco plants of the specified color. Okay. And then we can say here, let alpha be 0.05. Even though they gave that to us, you should always state it in the beginning so you're not a cheater. Okay, and then we do plan if conditions are met, we will perform a chi-square goodness of fit test. Okay, so there is my procedure name, and then we do the conditions. So random, and we say plants were randomly selected for mating. Okay, or scientists mated 84 randomly selected pairs. Pairs of plants. Okay, and then large counts or large sample size, and we say, okay, what are my expected counts? So I have to calculate this now. So we say the expected counts, and we have to list them. Okay, expected counts, and what are they? So again, it's the claimed proportion. So we should maybe state the color. So green coming from here. Okay, green coming from there. Green would be, my expected count is 25% of 84, which is the sample size, which is 21. And then, 21. And then yellow-green, should be 50%, 0.50 times 84, which is 42. This is my expected count. And then last one would be albino, and my expected count here would be, again, 0.25 times 84, which is 21. Okay, so you say, since all expected counts are at least 5, the condition is met. Okay, the large counts condition is met. So the sampling distribution of the sample statistic chi-square will follow an approximately chi-square distribution. That's what it means. Okay, and then independence. And did they say that? Interesting. I don't know anything about independence here. Okay, but what we can say is, if you want to do 10% condition, but this is not really sampling, is it? Randomly selected pairs. Oh, I guess random selection. Yeah, let's do 10%. We can say, let's say we have to assume, not it's safe. Let's say we have to assume that there are 840 plants in the population. And then we have to say something like individual offspring inherit their traits independently. Okay. This I just added. Okay, let's say that. All right, and then say do chi-squared statistic is the sum of observed minus expected squared over expected. And you would get this, 23 minus, I expected 21 over 21 squared plus, and since there's only 3, you should write all of them out, okay? There's no reason for you to do ellipses and stuff like this. Over 42. And then plus 11 minus 21 squared over 21. Remember, we're coming from these numbers here, okay? So 25%, 50, and 25, those are my claims that led to these expected counts, and the observed counts were 23, 50, and 11, okay? And if you do that math, you get this, 6.476, all right? And if you go on your calculator and do the test, you get a p-value of the probability that chi-squared is greater or equals to 6.476, which is 0.0392. And how many categories were there? 3. Okay, there were 3 categories, 1, 2, and 3. So my degrees of freedom is 3 minus 1, which is 2. Okay, this tells me how that happened. So you must list the degrees of freedom when you do this, just like we did for test of means. Okay, and now we say conclude, and we say since the p-value, which is 0.0392, is less than alpha, which is 0.05, okay, we reject the null hypothesis. Okay, so we have sufficient evidence to conclude, and now we're talking in terms of our alternative hypothesis here, okay, that at least one of the color distributions is incorrect, that at least one of the claimed distributions of color is incorrect. Okay? So, based on our sample data, something's wrong, and if you went on your calculator and you looked at the contributions, you get this for your contributions, okay? There they are. And the biggest contributor or component of the chi-square statistic, so we call these contributions or components, the biggest one is this. And that makes sense because for albino, the number of observed plants and the number of expected plants differed the most. So I can easily say that albino plants' contribution to the chi-square statistic is the biggest, meaning the biggest discrepancy is there. So if I want to do some follow-up analysis, which is something we'll talk about next section, if I want to do follow-up analysis and do further investigation, I would go and see what's going on with the big difference with albino plants. Okay? So they're called components or contributions, those numbers. And I showed you in the calculator tutorial that you can see those when you do your test. I hope this video helped you guys.